This is our 9th lecture in topology, and in this lecture we're going to talk about quotients. Now, some of you might have seen quotients in an algebra class when you talk about the quotient of a group by a subgroup, for instance. It turns out that there's also quotients in topology, and in fact there's quotients in many areas of mathematics, but topology is one of the places where you also have quotients. But they're going to be defined a little bit differently. So let's recall what an equivalence relation is. I want to discuss this. So just as a reminder, you talk about equivalence relations in some kind of proof writing class, or maybe a number theory class, maybe an algebra class. So I'm sure you've seen equivalence relations before, but as a quick reminder, an equivalence relation, let's call it tilde, on a set X. So here we just have a set. There's no topology. Let's forget about topology. Let's just talk about it as an operation on sets. So an equivalence relation, usually this is the symbol we use for an equivalence relation. So an equivalence relation is a subset of the product. So this is X times Y. This is the Cartesian product. There is no product topology here or anything like that we've talked about. We're just working with sets. It's a subspace of this. So this would mean that the equivalence relation, it's a subset of X times Y, some subset. And so tilde consists of pairs. You can say A comma B, where each of the two coordinates is an X. So that's what tilde consists of. Now, to be an equivalence relation, it has to satisfy additional properties. And the properties tilde satisfies are, so here are the properties. So the first property is X comma X is an element of tilde. So this is called the reflexive property. And the shorthand notation that people use is we write X is related to itself. That's what we say, X is related to itself. That's the way we write it. But formally speaking, you're saying that the pair where both of these are the same is an element of this relation. Then the next property says that if X comma Y is an element of tilde, then flipping them the other way around is an element of tilde. This is called the symmetric property. And the shorthand is to say X is related to Y, then Y is related to X. That's the way we usually prefer to use the notation. It looks a little bit nicer. And then finally, we have the transitive property that if X comma Y is in the relation and Y comma Z is in the relation, then X comma Z is in the relation. And here we write this, X is related to Y, Y is related to Z, X is related to Z. So when these three properties are satisfied, this one is of course called the transitive property. When all three properties are satisfied, we have something called an equivalence relation. And then we have these things called equivalence classes. Equivalence classes. So the way this works is we're going to suppose tilde is a relation, is an equivalence relation on a set X. So we're going to assume all of these properties. Then for any element in X, we define the class of A. So this is what we call the class of A, and it's equal to, by definition, this is the way we define it, the class of A. This is the collection of all elements in your set which are related to the A, that are related to A. So you can also write, if you want to, you can also write it like this, if you want to. You can interchange them because of symmetry, so it does not matter which way you write it. And also, just to note something, an element always belongs to its class. So that's just something to note. This follows from the symmetry property. I'm sorry, that follows from the reflexive property, that X is always related to itself. So the class of A is the collection of elements that are related to A. So A is always related to itself because of the reflexive property. So A is an element of its class. Sometimes that's the only element in the class, but you always have that, so it's not an empty set. And then the follow-up result is the equivalence classes partition X into disjoint subsets. So if you find the classes, the equivalence classes, they have to partition your set into these disjoint subsets. I'm going to give you a very easy example. This is probably something you've seen in a number theory course. It's a fairly interesting example. It's not too trivial and it's not too hard, and it nicely illustrates the idea. So in this case, we're going to let X be the set of integers, and we're going to define, so tilde is going to be the collection of pairs of integers. So it has to be a subset of the Cartesian product. So a relation is a subset of the Cartesian product. So pairs of integers. So they're both coordinates are coming from X, and the property here would be that 3 divides the difference between n and m. So 3 divides the n and m. So it can be shown, so the shorthand, so I'm going to show you the shorthand way we say this. So we usually do not write all of this. That's too much to write. So usually we say it like this. We say that n is related to m if and only if 3 divides their difference. That's usually the way we write it. So whenever we write something like this, it's understood that we're defining a relation on our set. So by definition, it's going to be the set of pairs, and then you say that n and m are going to be a pair in the relation when this condition is being satisfied. Okay, so for example, you would say that 2 is related to 5. You would say 5 is related to 2 because here the difference is -3. That's divisible by 3. Here the difference is 3. That's divisible by 3. 3 is related to 0. Okay, and so on. So when you write out the relation formally as a set of pairs, you would write 2 comma 5. You would write 5 comma 2. You would write 3 comma 0. You can write 1 comma 4, and so on. So these are just some of the different ways you can write it out. The difference does not have to be, maybe to do something more interesting, maybe you have, let's say, 7. The difference here is not 3 or -3, it's 6, but 6 is divisible by 3. So tilde as a set will be all of those pairs. So that's what we're saying. And let's find the equivalence classes of these. So let's find the equivalence class of some number, let's say 0. So the equivalence class of 0 would consist of all elements in X, or you could say, let's say all integers in Z, so that 3 divides n minus 0. Because you're saying, you want to say n is equivalent to 0, which is another way of saying 3 divides n minus 0. This 3 is just arbitrary. We just made up a number for the purposes of an example. So if you're wondering where it comes from, that's just an example. So, and if you write it out, so all numbers, so 3 divides n, so all numbers divisible by 3, so you would have 0, 3, 6, 9, and then you go the other way. This would be -6, -9. So that would be all of them. Okay, so this entire thing, this is what you call the class of 0. Now, if you pick any number in this class, let's say you pick 3, and you were to write this out, then this would be the set of all integers, so that 3 divides n minus 3. So here you would have n is equivalent to 3, so you want 3 to divide. So by definition, n is related to 3 if and only if the difference is divisible by 3. And if you write this out, you would get, it's the same thing, 0, 3, 6, 9. And the reason for this is because this 3 is already chosen as an element in the other class. So if you were to pick anything else in this class, you would get the exact same class. Now, if you pick something that's not in this class, then you get something that's disjoint. Okay, then you would get something that is disjoint. So for example, 1. You can see that 1 is not in this class. And if you write out 1, this is what you would get. You would get 1, 4, 7, -2, -5. You get all of those. And so you have these numbers, you have those numbers. So if you take a number that you have not seen yet, which is 2, then you would get 2, 5, 8, -1, like this. So that's what you would get. And you can check that now every number, every integer is among these three classes. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So all of the integers. So the equivalence classes is the class of 0, the class of 1, and the class of 2, and those are it. So there's 3 of them. There's 3 equivalence classes. And they are disjoint. They do not overlap. As you can see, they do not overlap. And you can say, well, what about something like the class of 3? Well, you can use the class of 3, but the class of 3 and the class of 0 are the same thing. They're equal. They represent the same class because 0 and 3 are related to each other. So they end up representing the same class. So you can sometimes use different integers to represent the same class, but the class as a set together will be the same. So there's only 3 classes here. So this is like a nice, fairly simple example that illustrates this idea of an equivalence relation and how the classes that you get from the equivalence relation, they partition your set. And now we're going to do something very similar in topology. So we're going to apply this to a topological space. So now this is what we're going to do. We're going to say let X be a topological space and tilde an equivalence relation on X. Okay, so I'm going to, so the notation that we use, so this is the notation. So this is X mod tilde. Okay, you read this as X mod tilde. This is different. So when we use complements, we write it like this. So the line, this is the forward slash and that's the backslash. This would be X minus A. I'm not a fan of writing this because sometimes it's confusing. It might get confused with something else. I prefer to write it like that. So X minus A. So this is the mod. And what is this? This is the set of equivalence classes. So in the previous example that we just did, we had an equivalence relation on the set of integers, and there were 3 of them: the class of 0, the class of 1, and the class of 2. And if you want to write them out even more explicitly, this would be a set, and then you open these up what they mean as sets. So this is quite, so it's like a set of sets, and then this would be 0, 3, 6, and then this one would be 1, 4, 7, and the other one would be 2, 5, 8. So that's what it would be. So the Z mod, the equivalence relation, would be a set consisting of 3 classes, and the classes themselves are sets. So this actually kind of goes back to what we were saying the last time. Sometimes when you focus too much on the set theory, it's a little bit confusing because there's so much going on. Oftentimes sets consist of other sets, and those sets contain other sets. So that's why we talked about universal properties, where you kind of focus on the main property and sort of forget about what something is as a set. But for the time being, I want to introduce for you this thing called the quotient by using various set operations, and then we'll discuss a universal property, which is a more abstract way of describing what it is and what property it has. So we have a topological space. This is an equivalence relation on X. This is the set of equivalence classes. And what we would like to do is we would like to topologize the set of equivalence classes. And we want to topologize the set of equivalence classes. So at the moment, so far, it is just a set. It's just a set. This is just a set, nothing else. It does not have a topology yet. X has a topology, but X is also a set. So you ignore the topology, you look at X as a set, you find X mod tilde, the set of all equivalence relations, and now you have this set of classes and you want to topologize it. So here's how you do it. So we have, so observe, we have a surjective map. There's this obvious surjective map, which we're going to call pi again. And this is the map that goes from X to X mod tilde. And the map here is very simple. Pi of an element goes to its class. Okay, so in words, so to say it in words, quite simply, pi maps an element to its class. So it maps an element to its class. And the reason why it's surjective is just has to do with the fact that every equivalence class is by definition of this form, right? That's just by definition. All classes look like that. So you are certainly mapping. Now note, if x1 is equivalent to x2, then pi of x1 becomes equal to pi of x2. So equivalent elements in X get mapped to the same point. So you see, the idea is you want to think of these classes as points in some new space, which might be a little bit confusing at first, because this is like an entire set of objects. It's like an entire set of elements, but you want to think of it as a point in some new space. So points that are equivalent in X, they get mapped to the same point over here. This is called the quotient. This is sometimes called the quotient of X mod tilde. Okay, so how do we put a topology on this? So it's reasonable. So it is reasonable that pi should be continuous, should be a continuous map. For the simple reason, because we want the quotient, since it's coming from X, to be somewhat similar to X itself. So this mapping should therefore be continuous mapping. So if it's a continuous mapping, what do we require? So we declare, so this is the definition. So we say that U, so a subset of the quotient, so you have to understand that this is now a set of equivalence classes. So it's like a set of sets. It's a set of equivalence classes. So we say that a subset is open. So you say it's an open subset if and only if, well, if you want this mapping to be continuous, then what's the requirement for continuity? When you pull it back, it should be open. So you say that a subset is open if and only if pi inverse of U is open. So the pullback of an open set should be open. So you define something open if it pulls back to something open. And you can check that this is therefore this puts a topology on X. This puts a topology. So that's not difficult to check why this now topologizes. So the requirements for a topology will now be satisfied. So maybe make this proposition. Maybe this can be like an exercise, perhaps. So the above definition of open puts a topology on X tilde. So I would say it's a little bit easier than the product space, because in the product space, we use the topological basis. Here, we're not using a topological basis. We just say that something is open if and only if it pulls back to an open set. And furthermore, this projection map is continuous. Now, the fact that it's continuous just follows immediately from the definition, because if you pick an open set in here, by definition, an open set is something that pulls back to an open set. So the topology is put on here specifically so that the projection map is continuous. So it's clear it has to be continuous. The only thing you have to check is that this way of defining an open set puts a topology on the equivalence classes. So now we have a topological space. And I want to look at some examples. So let's look at this very, very easy example, and then we'll look at more interesting examples. So here's an example. So let X be the closed unit interval. And tilde is defined as follows. So here's what you do. So if X is a point in this interval, then x is only related to itself, only related to itself. So if x is in here and x is somewhere inside the interval, then x is only related to itself. So here's a picture for what we're doing. So here is our interval from 0 to 1. And we're saying that if you pick x, so in an equivalence relation, you have to say what x is being related to. At the very minimum, it has to be related to itself because it's reflexive. So we're saying that x, in this example, x is going to be related to itself. So if you pick some x that's between 0 and 1, you're going to make it be only related to itself. So this x is only related to itself. This x is only related to itself. And if x is 0 or 1, then you would say that 0 is related to itself. It has to be 1 is related to itself and 0 is related to 1. Okay? So in other words, so maybe this will make it easier for you. So if x is between 0 and 1, then the equivalence class of x is just a set containing x. Whereas the equivalence class of 0 and the equivalence class of 1, it's the same, and it consists of 0 and 1. Okay, so that's the way you do it. So the idea is that if you're choosing something between 0 and 1, you only make it be related to itself. Okay, only to itself. So the equivalence class of x is just itself. That's the only elements it's related to. But at the endpoints, you treat these as being the same. So this one and this one are made the same. So you kind of make these be the same. So, and then we can form and so what can we say? We say about this quotient, x tilde this relation. What can we say? More specifically, can we identify this quotient as a more familiar space? Because what exactly is this? So if you write out this quotient as a set, here's the way it's going to look like. It's going to contain 0, 1 together because they are related to each other, whereas everything else is just going to be by itself. So a half is just by itself, a third is just by itself, 1 over square root of 2 is by itself. So you see, if you have a number x, if it's between 0 and 1, it's only related to itself. So then its equivalence class consists of just a single point. But at the endpoints, they become the same. They sort of become the same. So as a set, it's this, right? So as a set. So as a set, it's not very interesting. So it's just a set containing the exact same collection. I mean, it basically contains the exact same points, and the one exception is 0 and 1, and they're now being paired together into the same class. So that's what it is as a set. But as a topological space, so can we identify this quotient as a more familiar space? So in other words, is there a more familiar topological space homeomorphic to this quotient? And you can try to use your intuition for what we're about to do. You see, if you have any point in the interior of the interval, it stays by itself. You're not doing anything with it. But the endpoints, they kind of come together. So you're going to therefore take this endpoint. Now you can bend this interval. So this topological space is homeomorphic to this, and you can keep on bending it until the endpoints they come together. So if you keep on bending them until the endpoints come together, because you see 0 and 1, they have to come together, you get the circle. So, and the answer is yes. Yes. This quotient is homeomorphic to the unit circle. This is the way we write the unit circle, S1, because it's a sphere of dimension 1. And the most common way we think of the sphere of dimension 1, we've said this before, this is the set of complex numbers with the property that the absolute value of the complex number is 1. It's probably the most convenient way of describing a circle as some kind of set with a topology. So they happen to be homeomorphic. So intuitively, this is clear. So intuitively, this is clear. But let us give a more rigorous justification. justification for this, and then we will get more intuitive in the other examples. So in this one example, I wanted to show you carefully how you would give a rigorous justification for this. And then in the other examples, instead of wasting a lot of time trying to write out a careful proof for why they're homeomorphic to a different space, it's going to be essentially based on the same idea. So here's the way you do it. So we need to find the mapping. So let me do it like this. So we want to find the mapping. So find some homeomorphism that will take x, so x mod tilde, and we'll map it homeomorphically to the sphere. So how do we find it? So let's draw the following picture. So this is x. This is our interval from 0 to 1. And then we have the projection map that maps every element to its equivalence class. That's the projection map. Then we have the set of equivalence classes. Okay, and then we have the circle. The circle. So as a set, these are complex numbers whose absolute value is 1. And so let's make the map. Yeah, we want the map to go like this, right? We want to find some kind of map. Let's call this map phi. So let's call that map phi. So we want to create some kind of map. We want this map to be a homeomorphism. And we also have a mapping from x to S1 directly. And there's a very straightforward way to do this by using Euler's identity. So recall, Euler's identity is e to the I theta is equal to cosine theta plus I sine theta. So, and that's going to give you a point. So if you have a unit circle, and this is theta, then that point will give you a point on the unit circle with that angle, because the real part, that's the horizontal component, that's cosine theta, and the imaginary part, that's the sine of the angle, that's the vertical component, and this is going to be on the unit circle. So theta, as theta goes from 0 to 2 pi, you go around the entire circle. Now, because we're mapping this from 0 to 1, we're just going to rescale everything by 2 pi. So here's the way the mapping is going to be defined. So let's give this mapping a name. I'm going to call this mapping f. And let's say what this mapping is defined. It's going to take a point, let's call it theta, that's a real number from 0 to 1, and then f of theta, it has to give us a point on the unit circle. So it goes from 0 to 1, but since we want it to go from 0 to 2 pi, all we do is we do 2 pi theta, we do e raised to the 2 pi I theta. Okay, and that's going to give us a point on the unit circle. Okay, so we have this function. So now, how is phi being defined? Well, phi is going to be defined in a very similar way as f is. So phi is going to be defined as follows. Phi will be defined as follows. So if the class consists of just x, so if the class is just a single point, so x is between 0 and 1, and we define phi of the class to be equal to e to the 2 pi I x. So it's being defined in exactly the same as this f is. However, if the class is the class containing 0, which is the class containing 0 and 1 together, so that's at the endpoints, then phi of that class, this is the exceptional class, so this is of 0, 1, it's going to be defined as e to the 2 pi I 0. It's just going to be defined as 1. It's going to be defined in 1. And notice there is no problem, because if you do e to the 2 pi I theta, if you set theta to be equal to 1, you have e to the 0, which is 1. If you set theta is equal to 1, that would be e to the 2 pi I times 1. But by Euler's identity, that is 1 again. So whether you use 0 or whether you use 1, they get mapped to the same point, which is 1. Okay, so if you want the picture, so maybe this picture will kind of help you see what's going on. So let's reformulate this with some pictures. So here's our interval from 0 to 1, right? That's our interval from 0 to 1. And we have a mapping f. And this mapping f takes that interval and it maps it to a circle. Both of these endpoints get mapped to 1 because e to the 2 pi I theta at the endpoints become the same. And this mapping phi is defined in almost the exact same way. If you pick a class, right, you pick a class here. If the class is a singleton class, so it's an interior point, then you just map it the usual way. And if the class consists of both points, then you just map it to this number 1. Okay, you just map it to 1. And this diagram commutes. So if you go pi and then you go phi, that's the same thing as going by f. Because you see, this mapping phi is essentially defined by the exact same rule as f. So this diagram will commute. This is the mapping that we have. And these two get glued together and they end up at the same point. And we want to show, so what's the goal? So we want to show, now f and the circle are not homeomorphic, right? This is not homeomorphic to that. The easiest way to see why they're not homeomorphic, if you're wondering, they're both are Hausdorff spaces. They're both connected spaces. They are both compact spaces. So how do you prove they're not homeomorphic? So the easiest argument I can think of is if you take some point in this interval and you remove it, then you disconnect the space into 2 components. Whereas on the circle, it does not matter where you remove a point. No matter where you remove the point, the circle stays connected. So there's a property that a circle has that this interval does not have. So that's probably the easiest way to see why the 2 spaces are not homeomorphic. However, we're not saying that the interval and the circle are homeomorphic. We're saying that this quotient is homeomorphic to the circle because the quotient is supposed to represent what happens when you glue those together. So when you glue them together, that is supposed to abstractly represent the circle. And so we're saying this phi is a homeomorphism from here to S1. So we claim phi from the quotient to the circle is a homeomorphism. So why is this? So homeomorphism, we have to check that it's continuous. So is it continuous? So is phi continuous? That's the first thing. So let U be an open set in S1. So you would say, so we need to check that phi inverse of U is open in the quotient. Now, since the diagram commutes, so that's just another way of saying that if you go directly by f, that's the same thing as going by pi and then composing with phi, right? That's what we mean. If you pick theta and you go through f, that's the same thing as mapping theta into the class and then going by phi. Because if you look at the way phi is defined, it's defined by the exact same rule as f is. So the diagram commutes. Since the diagram commutes, what does this mean? It means that so I want to pull something back, right? I want to be able to pull back an open set. So if I pull back an open set, that's the same thing as pulling it back by f and then pushing it by pi. It means that phi inverse of an open set, right? This is what we want to find. That's the same thing as, so we have an open set here, we want to pull it back. So you can follow the arrows. You pull it back by f and then you push it by pi. So you would have phi inverse of U and then you push it by pi. Right? You push it by pi like so. Okay? And you get this, right? Right, so let me just repeat that again. You have an open set, you want to pull it back by phi. So how do you do it? You can pull it back by f and then you push it forward by pi. And you end up in the same location if you pulled it back by phi. Okay, so is this an open set in the quotient? Is this an open set in X tilde? Right? So because we're claiming the map is continuous. So if this mapping is continuous, then if we pick an open set over here, it should get pulled back to an open set. So is this map continuous? So what's the definition of the topology? So by definition, of the topology on X mod tilde, phi inverse of U is open in the quotient if and only if. So let me just remind you what the definition of the topology is. So we have this mapping pi from X to X mod tilde, and then we say that something is open, let's say V is open in the quotient if and only if the pullback of it is open in X. So that's the way we topologize the quotient. So if and only if pi inverse of pi f inverse of U is open in X, right? I mean, if like, sorry about that. Let me do this again. This is confusing. So this is open in tilde if and only if pi inverse of phi inverse of U is open in X tilde, right? So let's see what that is in this picture. So we have our open set. We're pulling it back by tilde. I'm sorry, we're pulling it back by phi, and then we're pulling it back by pi, right? Pull it back by phi, pull it back by pi. So is that open? So by the diagram, that's the same thing as this, right? So you have an open set, you pull it back, and then, right, so I guess we've written it, I mean, I guess this is not really necessary. So by definition of the topology, we have to check if this is open. So this is open by definition if and only if, when you pull it back by pi, it's open in the set. But this, from the commutative of the diagram, if you go back like this and you go back like this, that's the same thing as going like this. So that's just F inverse. This is just F inverse of U. That's just F inverse of U. And small mistake, of course, open, this makes no sense. So this is open in the quotient if and only if pulling it back is open in X, in the original X. So is this open? Yes. So the reason why this is open, and clearly F inverse of U is open in X, since F from X into S1 is continuous. So F inverse, the pullback of an open set, is open in X. If you look at this function that we had in the beginning, this function, this exponential mapping, so we had this exponential mapping right here. This exponential mapping is continuous. So if you pick an open set, so here's like a quick summary of what's going on. You want to show, you want to show that phi is a continuous mapping. So you pick an open set in S1. So how do you show it's continuous? Well, you do the pullback. You take your open set and you pull it back, and it ends up over here. And now the question is the set that you get an open set? Well, how do you check? You then have to take that set and you have to pull it back one more step by pi, by the projection map, and then see if it's an open set in X. However, because this diagram commutes, when you take that open set in S1, instead of pulling it like this and then pulling it like that, you can just pull it directly by F. So you have your open set, and if you pull it directly using F, you will end up with an open set in X, because this function F was continuous from that space to that space, which means phi is forced to be continuous. So phi is continuous. So that's like the simplified version. It just came out to be a lot longer than I wanted it to be, but that's why that mapping is continuous. So phi is a continuous mapping. So I'll take this away because it's going to distract us. So phi is a continuous mapping. And then you have to check the other conditions. So phi is okay. So phi from the quotient to S1 is continuous. Is it a bijection? Is it a bijection? And the answer is yes, because, well, let me say it like this. It's a surjection, because any point on the circle can be written in the form e to the 2 pi I theta. So you can always find something in x that will get mapped to that point. And then you just project the point to its class, and then that class gets mapped to S1. So any point on the circle can be obtained from a class. You can always find the class that gets mapped to the point. So it is surjective. Now the question is it injective? Is it an injective mapping? Now here's the part where you have to be careful. F is not injective. So let me say this. It is clearly surjective. Surjective. Is it injective? So note, the function f from x to S1 is not injective. Is not injective. Because the endpoints get mapped to the same point, as you can see. The two endpoints collapse and they get mapped to the same point. However, phi is injective because in phi, these 2 points are now the same thing. They're put into the same class. However, is not injective since f of 0 is equal to f of 1. However, in the quotient, something else happens. However, phi from the quotient to S1 is injective since 0 is equivalent to 1. They're treated as the same thing. And so you're mapping this entire class to the same point. It's no longer the case that you have separate points. They're now being sort of put together and treated as the same point. So this means that you have, so this right over here, this is a continuous bijection. So it remains to check that the inverse map is also continuous, because that's the requirement to see that you have a homeomorphism. Now, there is a trick that we've talked about before that can save a lot of time. And the trick is you do not have to check whether or not the inverse map is continuous if you happen to know that this space is compact and you happen to know that this space is Hausdorff. Now we know that this space is Hausdorff because it's a subset of the complex plane, which is metrizable, so it's a metrizable space, so it's Hausdorff. This is a Hausdorff space. So the question is, why is the quotient compact? So the simple answer is that if the space is compact, then its quotient will also be compact. So since the original space that we used at the beginning, x, since this x was compact to start with, this quotient will also be compact. So taking a quotient of a compact space will result in a compact space. We'll see the reason for that later on. And because of this mapping is a continuous mapping, and we have shown that the quotient is homeomorphic to the circle. So you can see, fairly tedious to say all of that. So if we just rely on our intuition only, we can be a little bit more rapid. But I want to show you some additional examples, and I think I'll put one of them on the homework so you can try doing it, but you carefully write out the details to show the homeomorphism. But I want to show you some other ones. So here's some other ones. So additional examples. So in all of these examples, we're just going to rely on our intuition. And of course, one can write a more formal proof of the homeomorphisms, but as you can see, that takes more work. So in this example, let's say x is D2. So this is the closed unit disk. So 2 means it's two-dimensional. So this is a closed unit disk X. Okay, so this is a two-dimensional disk. So it's sitting inside R2. And this is what we're going to do. So we're going to say that if P is in the interior of X, maybe I should not say in the interior of X, if P is inside the open disk, then the class of P is equal to just itself. Okay, so P is only related to itself. And then you would say that if P and Q are on the boundary, then P is related to Q. So this point and this point are the same. And this point are going to be treated. So all of these points are going to be treated. You see, that's what we're doing. We're saying this and this are equivalent. This is equivalent to that, so therefore all three are equivalent. So anything on the boundary is just equivalent to itself, no matter where you're located. So anything on the boundary. Okay, so if you want to write out x as a set, it will consist of an interior point. So let's say 0, 0. That's an interior point. So the origin is just alone by itself. It's only related to itself. Or like you can have, let's say, 1/2, 1/2. That would just be alone by itself, right? That's just by itself. It's inside the disk because the sum of squares is less than 1, so it's inside the disk. So that's just, you see, the class, the equivalence class is just itself. It's only related to itself and nothing else. But when the points on the boundary, they all become into this one big giant equivalence class. So you can have 1, 0. So 1, 0 is referring to this point. Then you would have 0, 1, right? You would have 0, 1. You would have -1, 0. You would have 0, -1. And then you can have other points on the boundary. Let's say square root of 2 over 2, square root of 2 over 2. That's what happens when the angle is pi over 4, and so on. So all of this, you see, all of this is one complete class, right? This is one complete class of points on the boundary. So as a set, that's what it would be. It would consist of singleton sets of all interior points, and all of the points on the boundary are just put into this one big giant set of points, which are now identified as being the same. So as a set, this is complicated. So as a set, the quotient is complicated, right? It's a set of sets, complicated. But can we identify this space as a more familiar space that we're more comfortable working with? And use your intuition here. So perhaps you can see what's going on. You're taking all of this. So imagine that you're lifting up. So imagine this is made out of a rubber material, and you take this and you push it down. So you see it's being pushed down. You push it down, and then you have this boundary, and then keep on pushing it further down. So if you push it further down, it's going to go like this. And if you push it further down, it's going to go like that. And then as you keep on doing it, the thing on the boundary, it collapses down to a single point, and then it gets closed off. And when it gets closed off, you end up with something like this, which is, of course, topologically, that's a sphere. So you can show that x mod tilde is homeomorphic. So this is the notation for homeomorphism. Some people, I guess, use this symbol, homeomorphic to a sphere, as 2, homeomorphic to a sphere. So that would be a sphere. So that would be the space that we get when we do that. Of course, we're not justifying why it is a sphere. That will take more work. But at least intuitively, it makes sense that the quotient space should be homeomorphic to a sphere. Now, to show some more interesting examples, here's another example. So let x be the closed unit interval. So here we can actually create a nice family of examples. So this is the closed unit interval. And what we'll do is, as before, so an interior point, so in an interior point of the square would only be related to itself. And then you would say that any point on the left edge is related to the point on the right edge at the same height. So to show what I mean is, you see this point over here? So let's say, let me do it like this. So this corner point, let's use this corner point. That corner point, the coordinates of it would be 1, 1. And that would be related to 0, 1. However, you have this point down here, which is at 1, 0, and you have a point down here, which is at 0, 0. So these two are related to each other, but these two are not related to those two. So this one and these, they're not being glued together. This one is only being glued with that one. This one is only being glued with that one. The points that are inside are not being glued anywhere, and the point on the upper edges are not being glued anywhere. So then you have, and then let's say you have this one, let's say you have this point. This one is, let's say, 0, 1/2, and this is 1/2. So these are being glued together. So that's what we mean. Any point on the left edge is related at the same height. So it has to be at the same height. So here the height is 0, so it's related to the point at height 0. This one is related to this. So if you were to write this out as a set, this is the way this is going to look like. So if you pick an interior point, it's just the set of points that are related to it is just itself. So for instance, 1/2, 1/2, that's an interior point, so that will stay alone by itself. And the same thing is also true if you pick something on the upper edge. So let's say that is at, let's make that up, let's say that's at 3/4, 1, and this is 3/4, 0. So these are not being related to each other. So you're only relating the left edges, the left and right edges. The upper edge and the lower edge are not being glued together. So you would do it like this. So you would say that, so the point 3, 4, 1 is only related to itself. It's not related to the point which is below it. You keep those unrelated, 0. However, if you're on the left and right edges, then you start relating them together. So you would say that 0, 1 and 1, 1 get glued together. So you put them into the same class, and then you would have 1, 0 and 0, 0 as part of the same class, and so on. So that's what the quotient is as a set. Okay, that's what it is as a set. That's of course not very convenient to think about. So we can wonder, can we identify the quotient as a more familiar space which we're more comfortable working with? And I should say that when we're dealing with quotients, it's not always possible to identify X as a more familiar space. It's not always possible to do that. I mean, sometimes these spaces can be very, very abstract, and then there's no way to like visualize it as something simpler. That's not always possible. Sometimes it is, and if it is, then we take advantage of that. But that's not always the case. So can we see this as a more familiar space? So the idea is that symbolically the way we do it is like this. We draw an arrow going up and an arrow going up, and we do not draw anything over here. We're saying that this and this is to be glued together. And you can imagine if you start gluing those two edges together, you would end up with a cylinder. So you would say that this is homeomorphic with the cylinder, and the cylinder can be realized as this product space. It's the S1 product space 0, 1. So that would be one way to do it. So this is an interesting example. Now what we could do is we can return back to this example and we can change things up a little bit. So let X be the same space. The interior of the square would be related to itself, and any point on the left edge is related to the mirror point, let's write it as the mirror point on the right edge at the opposite height. Okay, so here what's going to happen is zeros, instead of being related to 1, 0, it would actually be related with 1, 1. So you would actually have this. And 0, 1, so I'll get rid of this one. I'll get rid of these. They're just going to get in the way. Yeah, I'm going to get rid of those. Okay, so this one is going to be related to this one. This one, let's make it blue, is going to be related to that one. Okay, and then if you have a point, let's say right here, it's going to be related. You see, it has to go like this. It goes in the opposite direction. So I'm not going to write it out as a set anymore. I think you get the idea of how to do it. So that's the way we form the equivalence relation, and we want to see what that is. So basically, the way people draw this in a shorthand notation, they make an arrow going up and they make an arrow going down. So it's almost as if you want to glue these together, but you cannot glue them like normally you do in a cylinder. You have to twist it before you glue it. So let me see if I can find a nice picture on Wikipedia that will show you this. Maybe there's a really nice picture. So I'm looking over there to see if they show you how you can do it, like some kind of animation. It seems they do not have an animation, but they at least give a picture of the surface. So that is a Mobius band. So let's show the Mobius band. I'm sure you've seen this many times. So topologically, that is a Mobius band. There it is. And the quotient that we described right now is probably the most common way that mathematicians deal with the Mobius band. It is possible to describe the Mobius band with some kind of parametric equations in three-dimensional space, and that's a great calculus 3 problem. So if you've seen things like that in like a calculus class, like a vector calculus class, when you talk about parametric surfaces and you practice parametrizing surfaces in space. So maybe you've had this kind of exercise where you have to find the parametrization of the Mobius band, but it's a difficult parametrization. You have to use sines and cosines and half angles and all of that. It's a lot more convenient to work with the Mobius band the way we're doing it. So it's sort of like a cylinder, as you can see, but it's being twisted before it gets glued together. So that's an interesting example. As you can see, this is far more easier of working with a Mobius band than some kind of parametric equations involving sines, cosines, and half angle identities. So this is far easier to use. And an interesting question to ask, it turns out that the Mobius band is not homeomorphic with the cylinder. And surprisingly, it is hard to prove. It has something to do with orientability. So it can be shown that the Mobius band is not orientable, whatever that means. So the intuitive understanding of not orientable means it has one side, whereas the cylinder has two sides. But as far as a mathematical proof is concerned, that's not very rigorous. And it's just interesting that when you try to write a rigorous proof for why the Mobius band is not homeomorphic with the cylinder, it really takes quite the effort to show that. But it's just a known fact that they're not homeomorphic with the cylinder. So you cannot, you might think that it might be a cylinder. You might say, well, maybe there's some kind of way of undoing a twist. Maybe you can, because when we deal in topology, you're not confined to three-dimensional space. You can work in any abstract space. So you can say that maybe in like 5-dimensional space or something, you can find a way to undo the twist and return it back down to 3-dimensional space. But that's what we're saying. There's no way to undo the twist. It will always stay there and it will not go away. So now the reason why this is sort of strange is because, so I just want to tell you the part which I kind of find interesting. So this is the Mobius band. It's hard to draw. I guess so this is the cylinder. And the Mobius band, I guess the way you would draw it is somehow like this or something. I'm not even sure how to properly draw it. This is with a single twist. But you can do this. You can say, when you return back to the cylinder, so let's do it in a complicated way. When you glue this edge to this edge, instead of doing a half twist, when you do a 180-degree revolution of the paper to glue it to that edge, what if you do a 360-degree revolution? Because you can imagine twisting it twice and then returning back in the same direction and it's properly glued together. Then you would get like a picture of a cylinder with sort of like a twist. It's sort of like two twists in the cylinder going around, right? So you can kind of say that it's being twisted like twice. And it turns out you can show that this object is actually homeomorphic with the cylinder. I mean, it has to be, because you did the two twists, but it's like when you look at that, you might be confused. You say, how can this possibly be homeomorphic to that? Because once you have this object, you cannot bend it in three-dimensional space anymore and turn it back to something like that. So, but it happens to be. You can undo the double twist in like 5 dimensions and make it look like that. So yeah, I mean, that's just something interesting. So anyway, so that would be the Mobius band. Now, in the next example that I want to show you is, let's return back to our unit square. So that's our unit square. And let's do this. So let's identify these, and then let's identify these like this. So what does this mean? This means if you have a point on the upper edge and a point on the lower edge, they're being glued together. And if you have a point over here, it's being glued to a point over here. And then there's something special about the corner. If you have this corner point, well, this corner point is being identified with that corner point, because as you can see, like this edge and this edge are being identified. So if you're up here, these are being identified. And then since this edge is being identified with this edge, this left point therefore has to be glued to that point. And then because the left edge and this edge are being identified, these two have to be identified together. So you have this object. So what would be this? So if you write it out as a set, let me just show you some examples. If you have an interior point, let's say 1/2, 1/2, that's just related to itself. So its equivalence class would just be itself. If you have a point on the upper edge, let's say this one, but not a corner point, let's say this one. So let's say that point has coordinates So let's say x is 3/4 and the value of y is equal to 1, then it's identified with the point down there, which is also 3/4, and the value of x is 0. So these are being identified. Then the points on the right edge and the left edge are being identified. So this one and this one get identified together. So this and this, let's say this is, so let's say we have, let's say this is x is 0 and this is 3/4, and here x is 1 and this is 3/4. These get identified together. And then also the 4 corner points, so 0, 0, 1, 0, 0, 1, and 1, 1, they get all put into the same class. So they all get identified together. So this is your space, and you have a mapping from X into this space where every point is set to its equivalence class, and then you topologize, the quotient by saying that so a set of equivalence classes is open if and only if, when you pull it back by the projection map, it's open in X. So that's what this quotient is. It's the set of sets, right? It's the set of sets. Some of them are singleton sets. Some of them are sets containing 2 points. Some of them are sets containing 4 points. So that's what it is as a set. And then this is the topology. You say something is open if and only if it gets pulled back to something open in X. And the question here is, of course, what kind of space do we get? Is there a more familiar space? So the way you see this is you glue these edges together. And when you glue those edges together, so you glue this edge with this edge, when you glue them together, they give you a cylinder, as we saw before. And then you take these two edges, this edge, and you glue them together. And you can see if you glue them together, you get a torus. So let's see if we see a nice animation of this, perhaps on Wikipedia. Maybe they have a really nice animation of this, hopefully. So then I do not have to try to draw a picture. Yeah, so here is a nice animation that they have here. So let's just wait till the animation reloads. So we have, here is our unit square. Then we take the opposite edges, we glue them together, and then we take those two circles, and then we glue them together, and that gives us a torus, a very nice looking object, and that's called a torus. So this is a topological torus. So you would say that this space, so X ma tilde is a topological torus, and it's homeomorphic to S1 times S1. So I think maybe this would be a good homework problem, I think. So instead of doing homework checks on all of them, maybe I'll make this as a homework problem where you show carefully why that quotient, by kind of writing it out, where you define maps and all of that, where that quotient is homeomorphic to a product of two circles, and the product of two circles is a torus, as we've said before. So as you can see, the torus can be described in more than one way. It can be described as this product space, and it can also be described as this complicated set of equivalence classes with this type of topology. So they're both described, as far as topology is concerned, you're describing the same space. So this would be an example, and let me show you two more examples. I want to just show you two more, actually maybe three more examples. So let me just show you some more examples. So you can now, here is another one. Let's say it goes like this. So let's say these two are being glued together, but these two are being glued in the opposite way. Okay, these ones are being glued in the opposite way. So that would mean, for example, this edge point is related to that edge point, whereas this edge point, the blue one, is related to the one on the opposite side. And as before, the corner points all have to be related to each other. The reason for this is because if you have this corner point, this edge will relate it to this one, and then this one will relate it to this one, and then this edge will relate it to that one, and then you have the four corner points. So you can ask what kind of spaces this is. So if you glue these edges in the same direction, you end up with a cylinder. But now you have to be careful. You cannot glue this side of the cylinder directly. You cannot just bend it around, because that would mean the circles, they kind of go in the same direction. They have to go in opposite directions. So you have to bend your cylinder. So you can bend your cylinder without changing the topology. Okay, so you bend the cylinder. So then this circle is kind of going in this direction. Okay, and you want the circle to go in the opposite direction. So if you want to put them together, when you bend them, they go in. So by flipping this over, it now points in the same direction, right? You kind of flip it over. Now they point in the same direction. But you see, you cannot glue them. The moment, if you try to wrap it around, then the circles start pointing in opposite directions. So really what you have to do is you sort of have to take this piece of the tube, and then bend it through itself and make it come back. And then you end up with something like something that kind of goes back down to itself. It turns out this surface cannot be embedded in R3. So you cannot actually embed the surface in R3. Embedded means you cannot find a subspace in R3. So three-dimensional space, this is the space that we visualize, that is homeomorphic to this space that we get, to this quotient space. But you can get close, because you can see that as you try to pass it through itself, it intersects at certain points. And it's not supposed to intersect with certain points, because then the problem becomes that the places where it intersects, it's sort of those points are being glued together. But the interior points are not related to anything. So it's a little bit problematic. So this is really the best that we can do as far as visualizing it is concerned. So this thing is called a Klein bottle. This is the way it looks like. This is a very interesting looking space. This is called a Klein bottle. And people, so as it says, the Klein bottle was first described in 1882. So what we're doing is sort of classical topology by Felix Klein. And the way these surfaces came up is when mathematicians were trying to classify the different kinds of topological surfaces that you have, they realized that this is like one of the type of surfaces that come up. And you see, this says a two-dimensional representation of the Klein bottle immersed in three-dimensional space. So there's the difference between being immersed and being embedded. Immersed means almost as close as you can get to being embedded, but it does pass through itself. So this is the Klein bottle. So very nice looking surface. It's sort of like a Mobius band, but the Mobius band is not a closed surface. It does not close on itself. But this one, as you can see, that this one sort of only has one side. If you come in through this hole and you travel through this hole, you sort of end up inside of it, but you're not really inside, because then you can get outside of it again. Unlike a sphere, there's an inside and an outside. A torus has an inside and an outside. This one does not have an inside or an outside. It's just that. So this is another example of what we call a non-orientable surface, whatever that means. There is a rigorous way to define it, but it's what we call a non-orientable surface, which intuitively just means it has one side to it. And it is not homeomorphic with a torus. It has a hole in it, but it's not homeomorphic with a torus. So it's like different from a torus. And so when mathematicians were trying to classify surfaces, which we'll actually describe later in this course, they realized that such an object comes up, so you have to give it a name and you have to treat it. So this is what we get in this example. So maybe just show you one more example, just to finish with this. I want to describe one more type of somewhat interesting surface that's going to come up later on in the course that you can also not embed in three-dimensional space. It happens to be difficult to prove why you cannot embed it. I mean, it's not an easy theorem, but it's a well-known theorem that it's not possible to embed it. So here is another example. So in this example, we're going to have the unit disk again. So instead of the unit square, we're going to have a unit disk, and then the upper edge is going to go like this, and the lower edge is going to go like this. So what this means is this is sort of the place where everything gets cut off. And if we have a point over here and the point on the opposite side get glued together, the point over here and the point over there on the opposite side get glued together, this point and this point are not being glued together. They're just by themselves. So you're sort of folding it over this side to that side. And this is homeomorphic to a sphere, right? That would be homeomorphic to a sphere. So that's sort of easy to see. Now, the other one, which is a little bit different, is, let's say we draw the unit disk again. So this is, of course, the unit disk. So we draw our unit disk. And then what we do is we make, I think I should probably draw a better circle. We draw a better circle, a circle that closes up on itself. Okay, let's maybe do it a little bit better. There we go. So what we'll do is this upper half will go opposite of the lower half. They're going to go like this. So what that would mean is a point over here is related to the point on the opposite side, and the point, say, over here is related on the opposite side. So it's, you kind of want to make it like a disk. You want to glue this side to this side, but you have to twist it before you glue it. So this is sometimes called a cross cap, but we'll call it the projective plane. So it's denoted as P2. 2 because it's a two-dimensional object. So it's a two-dimensional object. It's called the projective plane, and just like the Klein bottle, you cannot actually embed it. But let's see if I can find a picture for you. Now, if you just search for the projective plane, there's many. Projective plane is a little bit ambiguous in mathematics. It means many different things. So maybe if we look for the cross cap, yeah, maybe if we look at the cross cap, we'll be able to find it. So let me just kind of go through. Yeah, so let's see if we can. I'm looking for a picture, but I do not seem to be able to find it on Wikipedia. So let me just find somewhere some kind of online image. So I think this is it. I think I found something to show you. So in this example, it's almost like a sphere, but it's bending and twisting through itself. So you can see it's sort of like a sphere. It is compact, sort of like a sphere, and it kind of bends through itself. So that's what it is. So you cannot embed it, but you can immerse it. So this is what we have. So this is the other example I wanted to mention. Now, here are some of the questions that I want to just quickly address concerning quotient spaces. So those was just a large list of important examples of quotient spaces. You can use quotients to produce some interesting spaces. So here's some interesting examples. I'm sorry, some important results. They're fairly simple. So here's a proposition that I wanted to mention. So if X is compact or connected, then X mod tilde is also compact or connected. This should intuitively be clear why that works, because the quotient space, it's essentially the original space where things are being glued together. So if the space is already connected and you're gluing things further closer together, it's almost as if this is becoming more connected. Not that there's such a term, but things are supposed to like sort of get closer together, and so it should continue to be connected. And compactness means that your space is so your space is sort of it's some kind of finiteness condition on your space. So when you're gluing things together, there's a lot of collapsing going on, and things get sort of closer together to each other. And as a result of that, the space should also be compact. So the proof of this is actually very easy. So I'll show you the proof. So I'm going to prove it to you in the case where the space is connected, and then you can prove it in the case where the space is compact. Very similar proof. So let pi be the projection map. Okay, so this is the projection map. And we will show that X mod tilde is connected. So we're going to assume that X is connected and then use that to prove that the quotient is connected. So here's how we do it. So the definition is with Clopin sets. So let C be a Clopin set in the quotient. So we have a Clopin set. And let's assume that it's the non-empty Clopin set. So then pi inverse of C is Clopin in X, because pi is a continuous map. If this is open, the inverse image is open. It's a continuous map. If C is closed, the inverse image is closed. So the inverse image is a Clopin set in X. Okay, so thus pi inverse of C has to be equal to X. This is a Clopin set in X, and it's not empty. It's a non-empty set because C is a non-empty set. This is a surjective map, so everything gets pulled back. You cannot be in a situation where you have something which is not the image of anything else, because this is a surjective map. So if the C is not empty, its pullback will be not empty. So this is not empty, and you have a clopin set in X. Now, because X is assumed to be connected, the only clopin set is X itself, or the empty set, but it's not the empty set. So pi inverse of C is equal to X. And now you apply pi to both sides. So thus, pi of pi inverse of C is equal to pi of X. And pi of X, the image of X, that's the quotient space, because pi is a surjective map. And you may wonder, are you allowed to remove them? Because in general, it's either this or this. Always forget which one it is. But because pi is a surjective map, that's just equal to C. And so your cloping set has to be equal to the entire space. And so what did we prove? We proved that the only clopin set in the quotient, other than the trivial set, the empty set, is the entire space. So that makes it a connected space. And you can also do the same thing with compactness. Now, a much more difficult situation, so a more complicated situation, is to ask the following question. If X is Hausdorff, is X mod tilde Hausdorff? Now, this one's more complicated. And intuitively, before we do anything, it should make sense that this does not have to be true, because you're gluing things together. Things that are separate in the original space get glued together. So things that are separated, they start coming together. So this may not necessarily be true. And I want to give you an example to show you how it does not have to be true. So here's like a very simple example. So let's say that X is two parallel lines. So if you want to be fancy, you can say it's R1 disjoint union R1, two parallel lines. But let's not go there. So it's two parallel lines. Okay, we have two parallel lines. So one of the lines, let's say this is one of the lines, and this is the other line. And here's what we're going to do. We're going to, so X is going to be this. So as a set, it's going to consist of X comma 0, where X is a real number, and then union X comma 1, where X is a real number. So let maybe redraw it. So this is, so two copies of the real line. You're going to take the union. This is, of course, the subspace topology of R2, because X is sitting inside R2. And what you'll do is, so here you have the origin. This is the special point. So let me fill it in. So this is going to be our special point. So this is 0, 0, and this is the other special point. This is going to be 0, 1. But what you'll do next is every other point gets, so these two get glued together, these two get glued together, and so on. So what you do is every point that's of the form X comma 1 is going to be related to X comma 0 as long as X is not 0 itself. So these are not related. So these two are not being related to each other. The points in red are related to each other. The points in blue are being related to each other. But the point on the origin and the point above the origin are not being related to each other. Now, intuitively, now maybe it would be a better exercise to make you write this out formally, but intuitively, what happens with the quotient, this line is being glued with this line. And you end up getting basically a line with like a double point. That's kind of what you get. So the quotient here, this is a line with a doubled point. I mean, if you want to visualize it somehow. So you have the real line, and at the origin, you just have these 2 points that are infinitely close together, but they're different. And the problem would be, is if you try to find, so notice what happens. If you draw an open set around 0, 1, and you draw an open set around 1, 0, these are open sets. So these 2 points are different. These 2 open sets are different because these 2 points are not being glued together, but everywhere else they kind of come together. So you can see that you cannot separate. So if you sort of try to find an open set that contains that point, it will sort of go like this. And if you try to find another open set that contains the other one, it will go like that. And they will intersect everywhere else except at these 2. So that's sort of like the picture, the idea of why this space, so this space, so this space is not Hausdorff. since the doubled points cannot be separated by open sets. It is still a T1 space, because you can see you can find an open set that contains this one but not that one, and you can find an open set that contains this one but not that one. But it is not a Hausdorff space. So as you can see, the Hausdorff condition can break apart if the spaces are not, so like it depends on the relation. It depends on the properties of this relation. So sometimes the quotient would be a Hausdorff space, but it does not have to be a Hausdorff space. So let us give a condition. So let us give a condition for when the quotient is Hausdorff, assuming X is Hausdorff. So here's the condition. So proposition. So let X be a Hausdorff space and tilde be a relation on X. So X mod tilde, so the quotient space, is Hausdorff if and only if, so if and only if the set of points, so let's write it like this, X comma Y in the product, so that X is related to Y, is a closed subset of the product. Okay, so that is the criterion. Okay, so that's the way it goes. So this is not exactly the easiest condition to use, but this is the proposition. And because we're lazy, we're only going to prove the easy half of the proposition. The other direction takes more work to prove. Not anything clever, but it just takes more work. It's fairly long. So we'll just prove it in one direction. So let's prove that if a space is, so if the quotient is Hausdorff, then, so basically, this is the set of points that are related to each other in the product space. So then the set of points that are related to each other in the product space must be a closed subset of the product space. So if this condition is verified, then the quotient has to be a Hausdorff space. Now let me just show you an example very quickly before we do anything with this. So here's perhaps an easy example to illustrate this. So here's like an easy example. So here's an example. So this was our earlier example where we have the line. This was our interval from 0 to 1. So that was X. And the relation that we had was that these two endpoints were being glued together. And we've said that the quotient was homeomorphic to the sphere, so it is Hausdorff. So it's a Hausdorff space because the circle, the one-dimensional sphere, the circle is a Hausdorff space. But let's check this condition. So let's draw the product space and find where all of the points are related to each other. So let's draw the product space. So if we take the product space, that will give us the unit square. Okay, so we would have our unit square. So that's our unit square. And okay, so that's our unit square. And we're going to construct the following set. We're going to construct the set of all points where X is related to Y. So all of the points in the unit square where X is related to Y. Now, keep in mind that X is always related to itself because that's the reflexive property. X is related to itself. So the diagonal would be part. So the diagonal would be part of that. Okay, this would be part of it. So the diagonal is part of it. But are there other points that are also part of this? Yes, because 1 is related to 0. So 1 is related to 0 and 0 is related to 1. So that means you also have this point and you have this point. So this set of all points that are related to each other looks like this in the product space. And this is a closed subset of X times X. So the quotient is a Hausdorff space. So this is like a fairly easy example to use. But in general, it's going to be hard to see because in this case, we can kind of draw it because this is a line. So product is going to be a square. But if X was a region in two-dimensional space, then this would be a four-dimensional object and you cannot really see it anymore. So it's not exactly the easiest condition to see, but it's some condition that tells you when the quotient is a Hausdorff space. Okay, so we have this result. Now, so I guess I should prove it, before I remove this, I guess I should prove it in the easy direction. So let's go ahead and prove it in the easy direction. So the easy direction is to show why it has to be a closed subset. So here's the way you prove it. Proof. So let Y be the quotient space. The quotient space. Okay, so that's the quotient space. So what are we going to do afterwards? So now that we have the quotient space, we're going to show, so let delta be the set of points, let's say P comma P. So this is the diagonal, which is in Y times Y, where P comma P, so that P is in Y. So this is called the diagonal in Y times Y. So since Y is Hausdorff, so that's what we're assuming, delta is closed in Y times Y. So now construct the map. So x times x into y times y. So how does this map work? It works very simply. If you take x comma y, you map it to the projection of x and the projection of y. So you always have a map, pi, from x to x tilde y, which is, I'm sorry, x tilde, x mod tilde, which is what you're calling y. So you have this projection map. So you take the first point, the first coordinate, and you apply the projection map. You take the second coordinate, you apply the projection map, and it can be shown that this is a continuous map. So if you're willing to accept that this is a continuous map, it's not difficult to check that it's a continuous map. So if you're willing to accept that this is a continuous map, so let's give this a name. Let's call it F. So F is continuous, and delta is closed in y times y. So thus, the inverse image of delta, this would be the set of points x comma y in x times x, that's the pullback, with the property that f of xy is equal to pi of x and pi of y, like this. Right? This is sorry about that. Sorry about that. That makes no sense. So delta, this is the set of points where both coordinates are the same. Both coordinates are the same. So then the inverse image of delta will consist of all points, so that f maps both of them to the same thing. So that means where pi of x is equal to pi of y. And two classes are equal if and only if they're related to each other. So that's what we're saying. So the inverse image will consist of all points in the product space where x is related to y. And this is closed. This is a closed set in the product space because this is the pullback of a closed set. So by continuity, this has to be a closed set. So at least we've proven this direction, and the other direction is more difficult to prove, but that's the criterion for when you know that the quotient is a Hausdorff space. So I would like to finish with the universal property of the quotient, because often it's not convenient to think of sets. So let us finish with the universal property of the quotient space. So it's going to be similar to what we did with the product space and the coproduct space. So I'll just write this down. And often this is more convenient, so you do not have to think of equivalence classes or anything like that. So here's what it says. Let X be a space and tilde a relation, an equivalence relation on X. There is a space, call it Q. So it's called the quotient space. So you see, previously we described the quotient space as a collection of classes with a certain topology. Now we're going to describe it in a more abstract way, not as a set, but as a topological space with some mapping property. So there's a space Q called the quotient space, such that there is a map, there is a continuous map. Let's call it pi from X to Q, with the property that if X and Y are elements of X and they are related to each other with respect to the equivalence relation, then pi of X gets mapped to the same point as pi of Y in the quotient space. And furthermore, Q is the optimal space with this property. So what does that mean? In other words, so what does that mean? So here's what it means. It means that, i.e., if there is another space, Y, with a continuous map, let's call it F, from X to Y, which also satisfies the condition that f of x is equal to f of y whenever x is related to y, then there is a unique continuous map, let's call it G, from the quotient space to y, which makes the diagram commute, which makes the diagram commute. So the picture here is, yeah, that took way too much space on the board, but the picture here is that this is X, that's the quotient space, there's a mapping pi. This mapping pi is a continuous mapping. It satisfies the property that any 2 points that are related in X, they get mapped to the same identical point in the quotient space. And this is universal. It's universal in the following sense. If there's any other space Y that has the same kind of property, that points that are related get mapped to the same point in Y, then this is optimal. So think of the supremum. Q is bigger than X. This is like the least upper bound, and Y is bigger than X. But this is the least upper bound, so this is smaller than that. So there's a mapping. You can find a mapping. You can construct a mapping from the quotient space G into Y that will make this diagram commute. So any mapping into Y factors through the quotient. So that is what the quotient space, that's sort of like the fundamental mapping property that it satisfies. And the proposition, of course, is Q exists, right? And it is unique. So it exists for any quotient. You always have the quotient space. And basically, the construction that we gave earlier is the justification for why it exists. You just have to show that the construction that we provided satisfies this mapping property. And then you have to show that it is unique. Unique would mean that any other space that is a quotient space and satisfies the same mapping property has to be homeomorphic to it. So if you have Q1 and Q2 and they both are optimal in this sense, then they have to be homeomorphic to each other. So this definition completely describes the quotient space in a more abstract way through a mapping property without describing what it is as a collection of sets and elements. So that's the proposition. I think it's very similar to the other ones. I think this will make like a good exercise problem for you to just check that the construction that we gave satisfies the required mapping properties.